For 4.6 billion years, our Sun has been a stable engine of nuclear fusion. It provides the energy and warmth necessary to support every living thing on Earth, creating an illusion that its presence is eternal. But every star is governed by its fuel supply. The Sun has a finite amount of hydrogen in its core, and once that reservoir is exhausted, the death sequence begins. Mercury will be the first to fall. Its proximity to the host star ensures it will be completely consumed. Venus is next to follow, vaporized as the expanding stellar atmosphere pushes outward. Current astrophysical models indicate it is extremely likely our own planet will share this fate. This event is scheduled 5 billion years in the future, yet astronomers can map these mechanics with high precision. Without a time machine, they have found a way to observe the end of a solar system long before our own begins its decline. Astronomers look to white dwarfs, stars the size of our Sun that have collapsed into spheres no larger than Earth. Many of these stellar corpses still host planetary systems. By tracking the mangled debris orbiting these remnants, researchers can observe the aftermath of a star's death in real time. These shattered systems provide a direct forensic record of the end state our own solar system is currently approaching. Recently, researcher Dr. Christopher Manser focused on a white dwarf surrounded by a glowing debris disk. Observing the disk's light, Manser's team found a periodic variation, spiking on a precise 2-hour cycle. At this distance, gravitational tidal forces would shred a normal asteroid. Surviving intact means it must be a high-density iron or nickel planetary core. To understand how a planetary heart could be stripped to its core and stay in orbit, we have to look back at the expansion that starts the destruction. The process begins the moment a star depletes the hydrogen in its core. Without the outward pressure of fusion to balance its gravity, the star's core contracts, while its outer shell expands into a red giant, growing thousands of times its volume, physically swallowing planets in the inner solar system. This isn't theoretical. Astronomers have directly observed a star known as ZTF SLRN 2020 in the act of consuming one of its own planets. When our Sun reaches this stage, the expansion will vaporize the Earth, leaving Mars as the new inner boundary of the surviving system. Eventually, the red giant sheds its outer layers entirely, leaving behind a tiny, hot core. This is the white dwarf phase. Because the star has lost a significant portion of its mass, its gravitational pull weakens. This causes the orbits of the surviving outer planets to shift and expand. As these orbits cross, they trigger massive planetary collisions. Large worlds smash into one another, generating a cloud of jagged asteroid fragments. The white dwarf's gravity pulls these fragments into tight orbits, grinding them down to dust. This dust forms a flat accretion disk around the dead star, mirroring Saturn's prominent rings. It acts as a gravitational blender, stripping away lighter silicate crusts, leaving only dense metallic cores behind. The white dwarf itself is a product of extreme physics. A single teaspoon of its material would weigh about 15 tons on Earth. This creates stratification. The powerful gravity sorts elements by weight. Light elements like hydrogen float to the surface, while heavy metals sink to the center. If planetary debris hits the star, its heavy elements pool in that top layer briefly before sinking. This creates a brief window for astronomers to identify exactly what that planet was made of by analyzing the light coming from the star's surface. Astronomers use spectroscopy to look for the chemical signatures of silicon, magnesium, iron, and oxygen trapped in this top layer. By calculating the ratios of these elements, they can reconstruct the chemical composition of a planet that no longer exists. Tracing the Sun's decline predicts our own eventual end, and it serves as a primary tool to determine if the recipe for an Earth-like planet exists across the entire cosmos.